go over parts of the eye. So the cornea, this is the transparent protective layer of the eye. It's just there to protect the eye. And then we have the iris. This is the colored part of the eye, and this opens or closes the pupil. And the iris, like if you have Face ID on your phone, the iris is what it uses to actually see it, because everyone's is different. That's the colored part. The pupil is simply the hole that allows light to enter, and it can dilate or contract or constrict or whatever, depending on how much light is there, because you don't want too much light to get in there. And then the lens takes the light that's coming through the pupil and focuses it onto the retina, more specifically the fovea of the retina. When the lens adjusts the light to put it onto the fovea, it's called accommodation. I doubt you'd be asked about that, but I figured I'd say it. The retina contains the visual sensory receptor cells, which are rods and cones, and the bipolar cells and the ganglion cells used to process the stimuli. So the fovea is the center of the retina, it's the center of focus, and it contains most of the cones. And then the lens focuses the light onto the fovea, and light is first sent to the back of the retina because the receptor cells are in the back. You'll see that in a few slides, but this is a diagram of the eye. You need to be able to label all of this, so yeah, just know it and know the function of all of these parts here. So this is the retina, as we said. So the receptor cells are actually in the back here. So cones and rods are in the back. So it actually comes in and then it comes all the way back here and then it comes back up. So the cones and rods and then the bipolar cells and then the ganglion cells, which eventually make up the optic nerve. So cones are the receptor cells. Cones see color. Just remember CC. Cones see color. They work best in bright light, and a lot of them are in the fovea. They connect the bipolar cells one to one. So one cone has its own bipolar cell, as opposed to rods, which have about 4 rods and 1 bipolar cell. So the information sort of gets distorted because one bipolar cell is taking it from 4 rods, which is why it can't take as much or as precise information as it could if it was just one bipolar cell for 1 rod. But we don't do that. We have 1 cone for 1 rod. Sorry, 1 cone for 1 bipolar cell. Rods are the receptors in the eyes that function in low light. They're scattered throughout the outer edges of the retina, and because they're on the edges, they're great for peripheral sight. That's what they're used for when the sun is out and whatnot. Set that 4 to 1 for the bipolar cells. So 4 rods will send their information to 1 single bipolar cell. The bipolar cells receive the messages from the rod messages. When I say message, I mean the impulses from the rods and cones, and then transmit them to the ganglion cells, which eventually form the optic nerve. And then where the optic nerve leaves the eye, there's a blind spot there because there are no receptor cells there. So summary of how it all works: the cornea protects the eye, it's transparent. Light travels through the pupil, which is opened by the iris. The iris is colored. The light travels through the pupil and is then focused on the fovea by the lens. The fovea has a lot of cones, which are great for bright light and color sight. So then the outer part of the retina is littered with rods, which are better in low light and are involved in peripheral vision. So the rods and cones are the receptor cells in the retina, and they deliver these signals to the bipolar cells, which then relay the message to the ganglion cells. So if you remember the order, it's bipolar then ganglion, because B comes before G. That's a way to memorize it if you want that. And then the ganglion cells eventually form the optic nerve, and then there are no receptor cells where the optic nerve meets the eye, so we have a blind spot there. The optic nerve goes to the thalamus, because everything goes through the thalamus except for smell. So it goes to the thalamus, and then it's sent to the occipital lobe to process the information. Trichromatic theory states that there are 3 types of cones: one that receive red, one that receives blue, one that receives green. And it states that all colors can be created by some combination of these three colors. So this is, you might have seen this is like from Microsoft Paint, I think, but that shows how like all, sort of everything can be created through the mixture of these colors. And then this explains color blindness, because colorblind people aren't actually like seeing the world in black and white. They just see only two colors or three colors. So they only have green and red, or just green, or something like that, when we say dichromatic or monochromatic. And this seems to make sense as to what they can see. So this is a really good job of explaining color blindness. And then opponent process theory was developed by Ehring, and this states that we have color receptors and opposing color receptors that work in the same complex. So we perceive color by a balance of the two. So there's the red and green complex, the blue and yellow complex, and the black and white complex. And you can memorize those colors go together because they're opposites on the color wheel. This explains the after image, and it also explains why we don't see bluish yellow colors or blackish white colors. Right? You just don't see these kind of colors because when the blue is on, the yellow is off. And when the white is on, the black is off. So they were like almost, if one's on, the other's not. So, but green and blue can both be on at the same time because they're two different channels. So I explained why we can see like, sort of it can be hard to tell like greenish blue, but it's always clear black versus white. So yeah, that's component process. And check yourself. You should be able to describe how we sense visual stimuli from the pupil to the occipital lobes. Explain trichromatic and opponent processing theory,